Okay, welcome to the CFA colloquium, everyone. Today our speaker is Roger Ramani. Roger carried out his undergraduate studies at Princeton and obtained his PhD from Caltech. He went on to positions at Berkeley and the Institute for Advanced Study before joining the faculty at Stanford, where he's a founding member of the Kavli Institute for Particle Astrophysics and Cosmology, current director of the Center for Space Science and Astrophysics. He has been a Gauss professor at Göttingen, a Spitzer lecturer at Princeton, visiting scientist at CSIRO in Australia and at the Arcetri Astrophysical Observatory in Florence. And he's a fellow of the American Astronomical Society, and along with was the recipient of the Bruno Rossi Prize in High Energy Astrophysics for establishing a theoretical framework for understanding gamma ray pulsars. He's currently probably doing a lot of things, but one of the things he's doing is a co-investigator on IXPE, the Imaging X-ray Polarimetry Explorer. He's the lead of the IXPE Science Advisory Team, and today I welcome here to CFA to tell us all about that, about IXPE, our first look around the X-ray polarized sky. So welcome, Roger.
Thank you, Pat. I think some legs to come. Now, I think I will lights down to the video mode if, okay. Can you bring the house lights down a bit? Great, thank you. So what I'd like to do is tell you about this mission, a little bit about its origin and how it came to be, but more importantly, the bulk of this talk is going to be about some of the first results from the first year. Now, I've restricted myself to results that have been at least on the archive, in most cases published. So there are other interesting, exciting things that I can't officially tell you about yet, but I hope that I can encourage you, even with the results that have already appeared in this first year, that we're a mission that's doing some interesting stuff. Half of the IXPE science team, which I won't list here. Although a small group of us, 10 of us, got together and started this project, it's grown appreciably. There's now over 150 folks spread around the world. And so that full collaboration list, many of who've been working quite hard on the data analysis, is not something I want to put up here. But you've got some of your own involved. Pat is the leader of the Supernova team. And there are many chances for folks to get involved at IXPE if we can go ahead with a guest investigator program, which we hope to have. So I'm going to kind of talk about this mission using as a bit of a gimmick the letters of the initial as a rubric to remind myself to tell you about different aspects of it. So I'll start with the X and the P. That's for X-ray polarization. And I first need to convince you that this is worth doing. Why should we bother? Well, okay. At CFA, of course, you're all convinced that X-rays are important, so that shouldn't be necessary. But polarization does have a rather peculiar role in this field, and it's worth saying a few words about why we're focusing on that. First, as you know, polarization is an exquisite probe of geometry. And given that our astrophysical sources are typically unresolved points, anything that can tell us about the geometry of the system is helpful. Now, it's of course native geometry through scattering that we can see, but also the magnetic field geometry is particularly powerful at constraining the physics of sources, and the polarization signal from highly magnetized plasmas can be very strong. Now, why X-rays as opposed to the other bands? Well, here I would argue X-rays are critical because they probe right at the hearts of the accelerators. Certainly, if you're talking about accretion-powered sources, you need to have a deep potential well to get up to X-ray temperatures. So it draws our attention to black holes and neutron stars. But in the non-thermal regime, if we're talking about synchrotron radiation in particular, if you think about the characteristic magnetic fields that we have in these nebulae, milli-Gauss fields, then the kind of energies it takes for the electrons to get your radiation in the X-ray band are many TeV. So we're talking about high energy accelerators, high energy particles, and in particular high energy particles whose synchrotron cooling lifetime is measured in years for these parameters. So you're looking close to the accelerator, not at the outflow that's been around for a long time. You're looking near the site where these particles were accelerated. Thus, polarization as a probe of that environment is physically particularly interesting. And I think that's a little theme that I'd like to have come out during this talk. We're, with polarization, probing some new physics aspects of some of these sources, which is what, as a physicist, makes it exciting for me. Well, if it's so great, why haven't we done it all along? What's the deal? Why has it been such a long time in coming? Well, here's the point where we draw a little attention to some history and the fact that polarization has been measured. First measured in the early 70s and by Well, our PI, Marty Weisskopf, and his colleagues, here he is prepping for a launch at Wallops with sounding rockets, and they measured one source. They measured the Crab Nebula with its net polarization degree and polarization position angle. That's largely where the field stood for 50-odd years, not for lack of trying. I was on quite a few proposals that Martin put in, where requesting one mission or another to get an X-ray polarimeter on the sky. Happily, this last proposal was, I think, particularly good and was successful, but it has been a long battle to get polarization observed beyond this single initial detection. Now, to be fair, in addition to the crab detection, that initial discovery, there were a handful of useful upper limits, and there have been, over the intervening years, some other efforts. There was a recent CubeSat which took the technology that I'm going to describe to you today, that's being used on IXPE, and tested it out. And that did manage to reconfirm the crab result, but didn't really go much beyond it. And at harder X-ray energies, it turns out different technologies using the Compton effect can give you some polarization sensitivity. And so X-ray polarimetry does have a little more than that just initial crab detection, but in the classical low energy X-ray band, that was it for 50 years. So why so long? Well, I think it's fair to say that several of the large projects discussed at least having a polarimeter on board, but it's a specialized field and requires specialized techniques. And so when inevitably you run out of time, money, and mass, what's the first thing to go? It's the polarimeter. So the only way for us to make this successful and to get Martin back on the polarimetry sky after 50 years of trying was, I think, to have a dedicated mission. A mission such that if you succeed in getting selected, you will get polarimetry done. It will achieve. And that was IXPE. So it's a SMEX mission, a small explorer. Here's the general layout for those of you who like such things. As usual, grazing incidence optics. We have 3 telescopes. These are Mandrel-built mirrors done at Marshall Space Flight Center. I think it's 24 mandrels per mirror combo. Effective area is not enormous. We have a 3-meter extensible boom. So, and I think the net focal length is pushing 4 meters anyway, and then 3 equivalent detectors. 3 is an important number in this kind of polarimetry physics in particular, because you want to avoid any right angles. The quadrants are the death of polarimetry experiments because the systematics that print through from X and Y can be very severe for measuring linear polarization. So 3-fold, or as you'll see later, 6-fold symmetry is something that we tried to maintain as much as possible in the system. Okay. That's the general setup. Here's the physics effect. It's the photoelectron that we're detecting has a signal. Its conversion cross-section is strongly perpendicular to the incoming photon direction and has a cosine squared phi azimuthal variation, where, as you would expect, the photoelectron heads off in the direction of the initial electric field of the incoming wave. So if we can detect the track of the electron, it will contain this cosine, in a statistical way, contain this cosine squared phi signature, and we can use that to measure polarization. So an electron tracking detector will see events that will look something like this. The initial conversion will occur somewhere here. The initial photoelectron will head off in this direction. Multiple scattering will rapidly change that direction, and it will range out in the Bragg peak at the end where almost all the energy is deposited. Sometimes, if these are K-shell electrons, you will also have an Auger electron event. So these are the idealized, rather better than typical looking version of the kind of tracks that we're trying to measure. How do we do it? Well, the detector is really very, very clever. It's a gas proportional counter that's highly pixelated. So there's a beryllium window, the photon comes in, there's a gas volume, a thickness of about 1 centimeter of about 1 atmosphere of DME. And in that, you convert your photon to a photoelectron. The photoelectron gets drifted across to a gas electron multiplier of very high voltage across 2 sides of a copper plate. You get a shower of electrons, and then you read them out on this detector plane. Whereas you can see they're little hexagons for the pixels instead of little squares. So once again, we have avoided rectilinear symmetry all in the goal of minimizing polarization systematics. So that so-called gas proportional gas pixel detector is really the heart of this instrument. It's was developed by our colleagues at INFN in Pisa over quite a period. And I think they're really remarkable devices. I think a lot of the credit for the success of this mission has to go to these novel detectors. The way I like to put it is, these are the first time we've really been able to tell everything about every single photon that comes in. All right, to be fair, not everything is measured with the absolute precision you would like, but of all the quantities that a photon carries, of all its information, we've been able to grab all of that. In particular, momentum. So the momentum is encoded in the position in which the photon comes in. It's an imaging system. our grazing incidence optics gives us an image on the focal plane, and we can measure the position of the photon where it hit to about 120 microns with these detectors, which is about 6 arc seconds on the sky. Alas, the optics themselves are not good enough to take advantage of that 6 arc seconds. These relatively low expensive, low weight X-ray imaging optics really only have about a half power diameter of 20 to 30 arc seconds. 4 telescope modules were built. Strangely, the best of the 4 is the ground calibration spare, and I don't quite understand the logic of that. But we have 2 on the sky that are just under 30 and one that's closer to 20. Okay, the field of view is decent, 10 arc minutes or so, so we get an image of the sky with every photon detected there. In addition to, of course, momentum of photon, you have energy. So we do get energy resolution. It's a proportional counter. It's not great, but it's about 16% at 6 keV. It's certainly enough across the main IXPE band, which is about 2 to 8 keV, to have several different energy bands so we can measure strong spectral features, but more importantly, use that energy as a sorting mechanism. You'll see how that's important later. So energy, time. We time tag every photon. The dead time is pretty modest, and so in fact we get about 100 microseconds photon tagging, which is good enough for the kinds of things that I care about, like millisecond pulsars. So that's great. And don't forget, of course, the whole point is that we measure polarization, the electric vector position angle, or EVPA. That's everything a photon carries. So everything a photon that hits the detector plane that is detected gives us full information on the astrophysical source. That's a good thing. Now, extracting that information from the detector plane is a little bit subtle, and here's some work that I and my graduate student, now just finishing up, Lawrence Pearson, did. We took a look at the kind of events that you typically get. Not nearly as pretty as the example I showed you on the other page. Here are simulated in this case so that we can know the true signature of the events at low energy, 2.7 keV, up to a high energy, 8 keV. At low energy, you can see these things are just blobs. How are you pulling out any kind of direction out of that thing? It's a real challenge. By the time you get to 8 keV, there's clearly a Bragg peak, and so you'd really have some separation. You can begin to get a vector. The way in which the collaboration's default analysis work is they simply take these images and really quite rapidly on the fly take various moments of those images and weight them to try to select away from the big peak, that's the Bragg peak, so convert over here, estimate the long axis, say, okay, it's along that axis, and by a little bit of tuning, that series of moments gives you an estimate of the position of the photon and its photoelectron direction. But we realized that that was throwing away quite a bit of information, and so as the slide suggests, my student happened to be very interested in machine learning techniques and was pretty good at neural net analysis, and so we put together a neural net analysis technique. This is simulation-based learning, as it's called, and managed to use that to improve more info out of these events. You can't make a silk purse out of a sow's ear, and at these low energies, you only get a little bit of information, a little statistical bias towards the right polarization per event. But this is a game of statistics. You have a large number of counts for any good measured source, and statistically, you pull out the polarization signal. So here's the degree in which things improved. If the perfect signal was this double sinusoid of this black line, then the standard technique is this blue curve, and with the neural nets, we managed to make the red curve. And you might not be impressed. Well, you probably shouldn't be that impressed, because the real art of this kind of technology is not that you measure things better, which you do slightly, but more importantly, you know what you know better. We get very quantifiable and very powerful measurements of the accuracy of the reconstruction, estimates of the uncertainty of the angles that we have, both aleatoric and epistemic. So we measure the systematic and statistical uncertainties on the events very well, which means you can take a large number of events, combine them together, and learn things appreciably better. So the sensitivity of the system rises appreciably from the default measurement. Using the weights that we get from these weights, we rise up to a sensitivity of about here, where this is the absolute perfect sensitivity that could be achieved by the detector simply because energy is being run out the back. We only have a centimeter of DME, so we're not converting all events. As it turns out, this procedure worked pretty well and actually improved our energy resolution a bit from the blue curve down to the red curve, and even improved our angular resolution, our spatial resolution, I should say. That ends up being important for something I will not talk about today, but you can ask me afterwards if you're interested. And the reason that it's a little bit subtle is that the telescope mirrors themselves, that's a quarter of the half power diameter. The telescope resolution is way the heck up here. So making this little improvement, you might think, who cares? And it turns out to be important for something, but nevertheless. So here we are. We have IXPE, the spacecraft that we put together with these wonderful detectors and these three co-lined X-ray mirrors, and we got it ready for launch. So here's the mandatory, I guess, image of a spacecraft being mounted on top of its launch mount. There's the fairing in the background. This is a Falcon 9. IXPE is a rather peculiar thing to be launching on a Falcon 9. Maybe I can make that a little bit clearer if I can show you a diagram that's to scale. Here's IXPE, sitting in, the size of a big washer-dryer combo maybe, sitting in the size of a thing that could hold a school bus. Why did we do this? Well, as I say, that's a bit of a political thing. As you know, when you have one of the centers involved in one of these projects, it's politically expedient to use the local product, and here we had to use United Launch Alliance's vehicles, were the prescribed vehicle for IXPE's launch. That meant, for a small Explorer launch, a Pegasus. Now, you remember what the Pegasus was, a very successful vehicle got us New Star and several other missions, although it had a little difficulty toward the ends of its lifetime, but it's small. It's a plane-launched rocket, and so it takes a small payload to orbit, and we forced IXPE into that small envelope. We cut down mass, we threw away capability, we cut down effective area, and we did it. But we are living with the consequences, because when it was realized that this was no longer a reliable launch vehicle, and NASA said, okay, you can have a Falcon 9, which by the way ends up costing $10 million less per launch, so it was a good deal. You sit there going, why didn't we build something bigger? Well, one of the requirements of the IXPE mission to ensure that they would choose the Pegasus for its launch vehicle was it had to be in an equatorial orbit. X-ray astronomers know that the equatorial orbit's a good place to be. A low equatorial orbit keeps you away from most of the SAA, keeps the particle background down. And with this plane, you can of course launch out of Kwajalein Atoll, so you fly down from 8 degrees and you launch right over the equator, and there you have it. That was a mission requirement. So that ended up resulting in a sort of interesting thing with this tiny IXPE payload being stuck on the Falcon 9. When we got it launched in December of 2021 last year, it's a nighttime launch, 1 a.m. It was pretty spectacular. I got to go down and see it, even though there was COVID. It was a lot of fun, but I missed out on one thing I'd very much hoped to see. This is the smallest payload that the Falcon ever launched, and when they usually launch small payloads, they do what's called return to launch site. And so in that case, they do a boost back burn, the rocket comes back and lands on a pad near the launching site. And the thought of seeing this 15-story thing falling out of the sky, I thought would be great. However, it turns out because of a requirement of equatorial orbit, they had to use the full power of the mighty Falcon 9 to get our tiny little IXPE thing into orbit by doing this. As one of our commentators said, they did a power slide over Africa. So we come down from Florida, arcing down at its 20-odd degree orbit. When you hit the equator in front of Africa, you burn the heck out of it with the second stage and turn the orbit around to make it into an equatorial orbit. That's what they did, and it worked. So we have a beautiful low altitude equatorial orbit. IXPE unfolded correctly. This is a little bit of a nerve wracker. When the solar panels coming out is no big deal, but when this 1 point failure of this, this thing unspiraling and putting it up, that was a little bit nerve wracking, but it all worked. So there we go. We've got IXPE, and now it's time to talk about the science. As Pat mentioned, I and George O'Mat have sort of helped organize this science team, so it's been very interesting taking the range of interests that our colleagues have had and trying to figure out what a good science program would be. To give you a scope of what we're looking at, well, here's the E-Rosetta sky, and I've just laid down some of our IXPE first-year targets on that. Now, the size of the symbol is proportional to the exposure. You can, of course, see that the vast majority of the sources are along the galactic plane, but there are a significant number at high latitude. And I've color-coded them here by the type of source, really our topical working group name that is associated with the different sources. And well, I'm sure you can identify from position alone, many of your famous bright X-ray sources are being covered here. Because I'm going to come on to this very shortly, the symbols that have a box around them, those are objects for which we actually get extended emission, polarized emission, so imaging is pretty important. Keep an eye on that because that's going to play a good role in the next topic. So how do we know how we're doing? The first thing I want to mention is that the mission has to dump the data every orbit at Malindi in Africa, and we have a very quick on-the-fly look at the data, taking the entire detector, treating it as 1 pixel, averaging over all energies and just seeing is there any net polarization. That so-called quick look analysis is done within a day or so of the observation. We get that. And yet during the first year, a large number of sources pass 6 sigma significance for detection just in that quick look analysis. So I think we can already safely say that we've taken ourselves a good step beyond a single source measured 50 years ago. We measure a large number of sources of a variety of source classes. And of course, X-ray astronomers looking at these names will say these are all old friends, and that's because they tend to be relatively bright ones. But quick look is time, spatial, and energy averaged. And so there's a lot more to be discovered when you get down and actually break things apart. Now, imaging is particularly important, and that, by the way, is the I in IXPE, so I might as well call that out now. Imaging is powerful for several things. Of course, as Pat knows, it's wonderful for supernova remnants, extended objects, where the polarization is distributed across the face of it, or pulsar wind nebula, things I like to work on. But it's also important we have areas where it's just complex. There are multiple sources in a small region, and our ability to separate the different sources and measure the polarization independently gives us a multiplex advantage, but also, of course, cleans up our ability to measure backgrounds and really characterize what's going on for an individual source accurately. So let's see how that works. And we'll start with Pat's favorite, Cas-A. Well, our first actual science target with IXPE was the Cas-A supernova remnant, a beautiful Chandra image thereof. And we have some knowledge of what we think polarization does in these remnants. We weren't really sure before we launched with the X-rays, but historically it's been known that from radio astronomy that the magnetic fields are radial. I gave a version of this talk to a physics colleagues at Stanford, and immediately I was queried on that. Radial magnetic fields, what are you talking about? Have you discovered magnetic monopoles? No, I hasten to add here, when an astrophysicist says a radial magnetic field, they mean volume or flux averaged in some way. The fields are radial, which means they're kind of long loops. So not pure radial, I should caution that. In any case, in the radio, we expect that we see the magnetic fields are radially extended. We also have some idea of what the maximum polarization could be. Synchrotron theory tells you for a given spectral index how to calculate the maximum degree of polarization. And from the spectral index of different places of the nebula, the forward shock in this outer region here, the reverse shock in the inner part, you're going to get something about 75% for the maximum degree. Now, what would you naively expect for the X-rays? Well, if you got a tangled magnetic field and it hits a shock, you expect to compress that magnetic field and therefore get a largely tangential magnetic field. And so we would expect the X-ray electric vector position angle, which is always at 90 degrees to the projected magnetic field, to that would be radial. So that was our expectation. Now, any decrement from this polarization degree indicates turbulence, or at least complexity in the magnetic field structure, so that you're averaging out different directions and reducing the total polarized intensity. That's useful because that's a powerful measure of, through the turbulence, through the process we call diffusive shock acceleration, whereby we expect that turbulence is very directly coupled to the generation of the high energy particles and the efficiency of reflecting back and forth across the shock front. So we expect there to be a correlation of this decrement from the perfect polarization with high turbulence and hence high acceleration efficiency. All that was expectations. What happened? Well, here's Pat's group's result. With Cas-A, by using the imaging and using the energy resolution, we managed to pull out a signal. Here's the first thing. You may not, I'm sure you don't remember, but in that slide of 6 sigma detections, Cas-A didn't make the list. And that's because you take a big light bucket and average over the entire circular supernova remnant, there is no net polarization because it spatially averages out. In addition, it turns out there's a large fraction of the flux is thermal there. And the emission lines, which can dominate the flux in some energy bands, they're not expected to be polarized. So we use both the energy capability of IXPE to isolate a region between the iron lines and the low energy excitation lines between 3 and 6 keV that's mostly continuum dominated. And we use the spatial resolution to kind of spatially coherently average over the nebula. By the way, the image in the background there is the IXPE energy coded image behind the Chandra contours. The result is this. If you just look at the entire nebula, the polarization is not significant. That's a 1 sigma ellipse. But if you measure the tangential polarization, i.e. if you find the electric field going tangential to the surface and average that up over it, you get a very highly significant detection. So once again, we find that the magnetic field in the X-ray emitting region is radial. So whatever process, and there is some debate about what that process might be, takes the turbulent magnetic fields of the shock and stretches it out in the radial direction, is effective on a short length scale. Effective on a length scale of something like 10 to the 17 centimeters or so. And that's a bit of a puzzle, I would say, Pat. I don't think it's fully understood how you can affect that extension so quickly. There's alternatives, which we'll probably not talk about in detail, but you could imagine selective acceleration on the zones that do have more radial field. So there are other explanations for this, but it's a very nice datum that needs to be studied further. Now, second supernova remnant that we observed, similar story, once again taking an energy range which minimizes the contamination of the thermal line emission. Once again, for TICO, which has these very nice Chandra measured hard spectral filaments of synchrotron emission, it also does find a polarized signal. Again, it's polarized, and again, it is basically radial. In this case, though, the polarization degree is appreciably higher. In fact, rising to some 20% in some regions of the west part of the supernova remnant. I guess in the story that I was telling you before, you would interpret that as saying that the level of turbulence is lower, or that the characteristic length scale of the turbulence is longer, such that there is less averaging away of that polarization degree. But I think the main lesson that we should get here is probably the first thing that we observe with IXPE will tell us something, but it's not until we observe several objects within a class that we should draw any broad conclusions. I think you'll see that a couple times through this talk. The first discovery is always very exciting, but the second object doesn't always follow the behavior of the first, and that's an important lesson. Okay, let me move on from supernova remnants, sorry Pat, to talk about something that we are excited about as well. That's the pulsar wind nebulae. Of course, there's the CRAB, that famous first detection. We were going to look at that, and during the first year, we in fact have these three objects programmed. What I'm showing here with this circle is that half-power diameter of IXPE. So if you think about the CRAB nebula, these are Chandra images, of course. If you look at the CRAB nebula, it's very marginally resolved. You're going to have to do some careful analysis to pull out the different aspects of the nebula from it. By the time you get to Vela, you're in slightly better shape. And this is the cosmic hen, MSH 15-5.2. And at that scale, you really can start to map the polarization in great detail. Well, so far we have in the can the results from the CRAB, and it confirms Marty's original measurements, which made him very happy indeed. He, in fact, went emeritus shortly thereafter, so I would call that a real success. Vela, perhaps even more exciting, as I'll show you in a minute, has measured and has enormous polarization degree. And this object, which I'm going to have a lot of fun with, hasn't finished its observation. It's only about half the data set's in. Let me show you the CRAB results and give you an excuse to introduce my graduate student, Josephine Wong, who's been working on techniques for pulling more signal out of the results. There is a paper that has been finally through the referee, or very nearly so, that will be appearing shortly, but since it's on the archive, I think I'm allowed to talk about the CRAB results, and in fact, these are a step up from what is on the archive. With the techniques that Josephine has developed, we managed to pull out both the polarization map of the nebula and improved resolution of the polarized signal of the pulsar. So here's a map of the magnetic field, and the basic thing you see is it's toroidal, right? You can see it's kind of arcing around as you might naively expect. There's one feature that's kind of amusing and maybe interesting. Take a look at the sides here. Do you notice how the toroidal magnetic field wraps around? Well, in this region here, it would be wrapping very fast. And so depolarization, beam depolarization, just the fact that within the IXPE resolution element, all the different position angles are present, causes it to be depolarized on the sides of the real nebula. Now, in this particular data set, it's not clear that we're detecting the jet yet, but we have good hopes of being able to pull that out with the deeper exposure. Here's the pulsed polarization signal in Q and U, and it's, at present, the initial observation with the CRAB was only about 90 kiloseconds, and it was before the telescope was aligned, so it's not quite the best data that we can get. We expect to do appreciably better in our next observations. But even there, we're detecting significant polarization, in this case, over 3 sigma in 4 of the phase bins. These are 2 sigma, the lighter greens. And the thing that's interesting to me is the background dots that you see there are the polarization that's measured in the optical band. Very nice observations by Gottfried Kalmbach almost 20 years ago now, that we have been puzzling over for the past 20 years and not understanding. What I find encouraging is, even with this initial IXPE measurement, we have several points that are several sigma away from the optical. And that, I believe, will give us some hope of finally breaking down and getting the geometry of the emission zone for the CRAB understood, because at least it's different than the thing that puzzled us for so many years. So that's good. I mentioned Vela as the other pulsar wind nebula that we measured. This one was a lot of fun. And in fact, the result was striking enough that we got into Nature for that one, so that's always good. Again, remember there's a maximum polarization degree depending on the spectral index, the classic Rybicki-Lightman result that you probably all remember from your mother's knee. In any case, that value, when you plug in the spectral index of Vela, depending on where you look, it's between 66 and 72%. Aha, what do we actually measure? 63% if we just do a bulk grid, and if we take the front edge of it, we get 70%. We are right up against the maximum polarization that can be allowed for that spectral index. So what does that tell you? Well, to me, it tells that in contrast to the supernova remnants, where accelerating the particles seem to critically depend on turbulence, here the particle acceleration must be largely turbulence-free. I would in fact argue that it's some form of magnetic reconnection. In the striped pulsar wind, you have magnetic fields of opposing polarity going out in the wind, and away from the equatorial zone, there's unequal amounts of the two polarities. So there's a strong background field that is preserved after you annihilate the remaining canceling field. And if the energy of that canceling field goes into particles, but it's organized by the background field, you could imagine a situation where you maintain very high polarization over large distances. But that's a supposition at this point, and we need to explore that further. But we're starting to get into the physics of relativistic shocks, and that's really good. Now, while we're talking physics, if you don't mind, I'd like to introduce something about magnetized thermal plasmas. I'm going to move away from those non-thermal synchrotron sources and talk about thermal sources for a minute here. As you may remember, when you have a strong magnetic field, the propagation through the plasma then occurs in the two modes, the ordinary and extraordinary mode. And those two modes have different cross-sections for the propagation. The extraordinary mode has a substantially lower cross-section once you're below the cyclotron resonances. What that means is if you're looking at a thermally stratified stable plasma where it's cold on the outside and hot on the inside, you inevitably look deeper in the X mode, and so the radiation is dominated by the X mode that comes out, the hotter zone. And so we expect polarization to be very high with X mode dominant for thermally emitting plasmas. And especially for X-ray binary stars, with accretion columns and such, the classical work that Peter Majaros and company did back in the 80s predicted polarization-like curves and polarization structure where the polarization degree was typically 70 to 80%. Enormous polarization. Therefore, when we planned for our initial IXPE year, we had several observations of these sources, often relatively short exposures. Now, there's a second phenomenon that I need to mention before I go on, and that is the birefringence itself affects the polarization vector direction. Now, as you go through a magnetized medium, that birefringence can then cause the polarization to track the magnetic field. In fact, for some of you know that there's, and again, my physicist colleagues take me to task for this, we call this in astrophysics vacuum polarization when you have a magnetic field that's higher than the quantum critical field. This is the field at which the cyclotron energy is equal to the rest mass. So above 4 times 10 to the 13 Gauss, we say that's vacuum polarization. They say, no, that's magnetized. The true vacuum itself is, of course, unpolarizable. So that is a point of difference. In any case, in either of the cases, through a magnetized plasma or a strongly magnetized vacuum, you will have the polarization tracking the magnetic field. Now that's important because if you get down to it, what that means is that will be true to a point where the magnetic field drops to the point where the process no longer works. For a neutron star, that means you have to go a long distance away from the very high surface fields. These numbers being quoted here, 10 to the 13 Gauss, are the dipole surface fields inferred from various measurements. But of course, you all remember that if you look at multiple moments, as you go to higher and higher multiple moments, they fall away faster and faster. If the surface fields of magnetars, as they are believed to be, are very complex, that means that the higher order multiples will drop off, and by the time you get to a large distance away, a simple dipole field will apply. Weaker, but simple. So what happens is that this so-called polarization limiting radius, the number of times the size of the neutron star that you have to propagate before things break free, it depends on the magnetic field and the particle energy, but it's several tens, which means that the fields have cleaned up and they're simple and dipolar. Let's see why that matters. Well, for the X-ray binaries and magnetars, it matters because the polarization degree, the fraction of it that's polarized, is set right down there at the surface where the emission is. But the polarization orientation is therefore set at the polarization limiting radius where it's dipolar. So we can have complex polarization at the surface, but simple polarization vector behavior. Now, here's the summary of the main results for several objects that I'll show you in a minute, and that is that what we found was, in contrast to the predictions, not 80% polarization, but 10 to 15%. Well, life's like that sometimes. But that 10 to 15% means that there must be some interesting additional physics going on. It's not 100% clear what's happening, and I'll show you 2 objects where our interpretation is slightly different, but the important effects involve what's happening right down there at the surface. A surface temperature inversion can certainly reduce that dominance of the X mode, so that's certainly a role. But even more interesting to me, at least, is the possibility that in some cases, the surface we're talking about is not a gaseous surface at all. It's solidified, it's crystallized into a solid. And so surface condensation can also affect that polarization. So let me give you quickly a couple of examples to kind of illustrate what I'm saying. Here's HERX1, our initial observation of HERX1, I should say. And if you look at this is a plot of the polarization degree. The polarization degree is the black curve. This is the so-called NDP 99, our sensitivity for polarization. it looks like a bit of a mess. When you decompose it, you can find that its polarization degree is high only when certain components are dominating. When this component's dominating, the polarization goes down. In contrast, if you look at the position angle, it's a little noisier than I would like, but I think you can convince yourself that it's relatively close to a simple sinusoid. And that's the basic story I'm trying to tell you. When we look at these objects, here's SEN-X3, we find that when some components dominate, say this red component dominates, you'll get high polarization. But that the behavior is complex and roughly follows the light curve, whereas the position angle, maybe a little less convincingly here, but statistically it's still okay, is a simple sinusoid. So, the surface controls the polarization degree, and something's complicated there. The position angle is controlled by the rotating vector model with a simple dipolar-like swing. Given time, I'm going to skip this. I was going to talk about mode conversion, but let me move on to a couple of magnetar results. So here's the first magnetar we looked at. This got published in Science, nice result. Spin period is slow, 9 seconds or so. Magnetic field well above the quantum critical field, so these interesting things could come into play. And this is the first object for which we found this behavior of polarization degree that kind of mimics the pulse, but position angle varying in a relatively sinusoidal way. So the basic story I told you is fine. But what about the amplitude of that polarization degree? That is not 0.8. That's only 0.15 or so. Something's knocking it way down. And the other thing that's interesting is if you look at the polarization as a function of energy, this so-called radar plot we show as distance from the center, the polarization degree, and position angle goes around the plot. Oh, of course, polarization, you only get 0 to 180. But in any case, what happens here is you go from low energy 2 keV up to our high energy 8 keV. The polarization starts over here, goes to 0, has a flip of 90 degrees, and then heads off that way. That's telling you that there's a mode change. You're going from X mode to O mode or O mode to X mode. It's not quite clear which, but you're definitely converting from one to the other as you go from the low energy part of the IXPE spectrum to the high energy part. Now, the fact that the low energy polarization degree is low suggests that it indeed is one of these surface temperature effects, temperature inversion or condensation effect, that O mode may be dominating. And that as you go to high energies, the resonant Compton scattering increasingly dominates the spectrum, and that must emit in the X mode in this case. But before you get to the conclusion that they're all the same, just like the supernova remnants, even the second object we looked at taught us something slightly different. So this is the second of the magnetars. This one is similar period, but even higher magnetic field. Hold on to that for a sec. And this is the basic result. In that kind of diagram, we don't have a mode flip. It starts off with the low polarization degree, and as you go to higher energy, it just gets stronger and stronger and stronger, heading off in one direction. What's our interpretation? Well, here's a diagram that I put together after some work that Tarola did. If you look at the magnetic field, here's log magnetic field versus log of the surface temperature. It turns out that the condensation track depends on what it's made out of. If it's made out of hydrogen, you've got to get way down here, but if it's iron, it's up in this domain. So there's a boundary between when things are solid or gaseous. If you look at classical pulsars, they're down here, magnetic fields of 10 to the 12th Gauss. They're cool, but they're safely above that. If you look at accreting neutron stars, they're hot as Hades, so they're way up here. They're going to be gaseous. Magnetars, interestingly, live in this transition regime. The first one I talked about is here. The object I'm referring to now, we measured 2 different temperatures on the surface, and they range from here to here. Aha. So maybe now we're getting somewhere. Maybe we're exactly at the place where condensation can begin to occur, at least at the colder parts of the surface, of these super strong magnetic fields, where the atoms are stretched out into very long cylinders and form a crystalline lattice. I think that's fun that we can be doing solid state physics from several kiloparsecs away. Anyway, I'm looking forward to more such observations. Now, let's dump the magnetars for a minute and move on to something that was recently a lot of fun. Everybody remembers the news reports where this, the bright source in the sky. Remember the boat of back last October, the brightest of all time. Anyway, as many did, we heard the IAU circulars coming out about 5 hours after the event and started paying attention, and we asked ourselves, can we do this? Well, before the launch of IXPE, we told ourselves we're probably not going to be able to get onto a gamma ray burst. It's got this long, flimsy arm. You can't swing that thing around. And it's basically scheduled to only be, the pointings are very long, typically hundreds of kiloseconds to megaseconds. And so we typically only schedule it once a week or so. However, when an event like this comes on, 10 times brighter than any gamma ray burst that's seen before, you at least try to bend the rules, and we were lucky. It turned out the timing was surprisingly good. By the time we got our TOO team together and said, okay, we're going to do this, about 24 hours after the burst itself. It turned out we were just under a day from the next upload, and we managed to dump the things on the schedule and get IXPE to turn to it. So we got onto it 58 hours after the burst itself occurred. And we observed for 2 days, so it took us to 107 hours. By the way, when we say the boat, I don't know if you've seen this plot before. Here's some famous gamma ray bursts, these little blips over here. Pathetic. When we get onto this guy, it's really booming. This was a strong one. And you can see it's definitely not just a once in a mission opportunity, but that may have been a once in a generation opportunity. So what did we see when we got to it? Well, we saw this. I've given here the image from IXPE on a log scale, and I've kind of broken it down by time. This is in hours after the burst itself. So burst, the label's not quite, so 60 hours after. Do you notice something? Well, you can see these rings expanding around it. Those are the dust rings. What we're looking at here is the burst occurred at very low galactic latitude. We're looking through the Milky Way. And so we actually see the scattering off of intervening dust, giving us a delayed version of that prompt burst signal itself. That was seen earlier than IXPE, of course. But I think the nice thing on our part is that with our 2 days of observation, just during our single exposure alone, you could actually watch the rings expanding on the sky, which is kind of fun. So the nice thing about this is it lets us analyze not just the afterglow, the light of IXPE 50 to 100 hours after the burst itself, but the prompt emission itself. What did we get? Let's be honest, it was only upper limits. Some people find these upper limits interesting as being model constraining. I'm a little less impressed, but anyway, we got less than 6% polarization currently from the afterglow itself. And then from the rings, which is I think the more interesting part perhaps, the prompt emission was less than 27%. Now, why should the afterglow be polarized? Do I have time to go through this? This audience knows all about gamma ray bursts. I probably shouldn't bother. But okay, I'll just say in a couple quick words. So here's the afterglows coming down. This is the previous brightest burst. Here is September 11th. So you know it's a good bit brighter. This is when IXPE got on it. This is a log time versus log flux. So it's fading fast. So you might ask, well, doggone it, why didn't you get on it a little bit sooner? I don't think it would have helped, and here's why. The polarization signal that you might expect from a gamma ray burst comes from the fact that you've got a relativistic jet expanding at gamma factors of order 100, as you here know. If on the surface of that expanding jet you have shocked emission where the synchrotron arises, you expect largely transverse magnetic fields, and if they're scrambled, what's going to happen from Doppler boosting is that relative to the line of sight, the place that you're looking down this jet, let's imagine the jet subtends this angle in the sky, as you look down the jet, the emission will be polarized radially to your line of sight. So when you first look at the burst, it's got an enormous gamma factor, and so the area that you observe on the jet is small. But as time goes on, as the burst slows, the area you observe grows. So think about what happens. When you very first observe, it's very nearly symmetric. You're fully contained within the jet. After a while, as you expand, you're dominated. There's more emission to the sides than vertically. The polarization goes horizontal, and then at this point it's equal, and then finally it becomes vertical again. So we expect the polarization to do this. Start off zero, low, grow, go through zero again, flip 90 degrees, then grow. So had we been able to get on the sky earlier with IXPE, say after 1 day, I don't think we would have seen polarization anyway. You might say, okay, maybe you should have waited for here, but look, it's getting fainter. I think we did just about as well as we could. You want to do better on a gamma ray burst? You better wait for a while to get another bright one, or you better get more effective area than IXPE has. Okay, I'm done with gamma ray burst. I'm now going to go a little extragalactic for a few minutes. We had some interesting initial results on blazars. These are the relativistic jets accelerated by black holes in the cores of galaxies, and we looked at some of the famous ones, the Markarians first of all. Markarian 501, this got published in Nature as a nice result. What we find is not that complicated. We find a polarization that's angled, that's lined up with the jet. That's good. We find a polarization degree in the X-ray that's several times that in the optical. And we think that that's interesting because it helps us discriminate models. The second one, we looked at Markarian 421, again, we found a jet polarization lined up largely with the jet and a polarization degree that exceeds that was seen in the optical. Theoretically, we have some understanding of what this means. We expect that it's telling us that we're looking at shock emission and that the prompt emission immediately after the shock, where the particles haven't cooled very much, that dominates the X-ray band. And there, the magnetic field is relatively organized. As you go downstream and the particles cool, turbulence builds, but of course that's the region where you're dominated by the lower energy optical millimeter radio band. So we would argue that, and at least the first author of this tells us that we have, by looking at these IXPE results, have selected an energy stratified chromatic shock model for what's powering the jets. I don't think anybody will find that radical. I also would guess that some people will not find that definitive, but it's a certainly good leading indicator that our basic story of shocks, internal shocks in the jets powering these particles is a good place to start. Okay, there is another addendum that I guess I allowed to mention because it was just a mention in a talk a week ago, even though this has not been published quite yet. Markarian 421, we looked at it several times as we look at these blazars repeatedly. They're very turbulent and varying. And we found something very interesting. During their third observation, we find that the electric vector position angle rotates. So the position angle in the sky during our 2 days of observation goes from here all the way up to there. Very rapid rotation. This phenomenon had been seen in the optical in the past. Optical monitoring programs have seen long rotations of the electric vector position angle, sometimes lasting many days, sometimes going through several cycles. The general inference is that these are probably associated with helical magnetic fields in the jets. Either those helical fields propagating through a standing shock, so the location of the phase angle of that helix varies over time, or perhaps a plasma-emitting blob oscillating, accelerating along that magnetic field line. In either case, we expect to get this sort of behavior. And once we're still studying this. It's got some interesting comparisons with what's going on in the optical, which wasn't rotating at that time at all, by the way, again suggesting that the locations of the X-ray and optical polarization are not co-located. That I think we're going to learn quite a bit more about the jet physics as we can see this kind of behavior occurring more often. I'm doing okay, but I'm getting near the end. I want to mention a couple more exogalactic sources. We did take a nice look at the Circinus galaxy, famous and one of the nearest AGN to us. This is an interesting object because it's a type 222. We're looking at it, we're looking at a very large angle, and so it's completely obscured by the dust torus. But the light that we see at high energies is then therefore reflected off in an outflow. And so with reflected signature, you expect polarization, and indeed we do. There's a very nice, it turns out the cold reflection seems to dominate in this case, and so there's a substantial, quite high polarization degree measured for this object with very high precision. So that's a reflected signal. Time to do black holes again briefly. SIGX-1. There are many possible sources of polarization in the system. The massive star accreting through the accretion disk with the jets. Well, certainly we expect at a bare minimum thermal polarization from the accretion disk itself. More realistically, if there's a corona above or below it, the scattered light in that corona will provide polarization. But we shouldn't forget that at some episodes, the jets are quite strong, may contribute polarization as well. And finally, for what it's worth, X-rays scatter off the companion star. That'll be polarized too. So what do we actually see? Well, the thing that's interesting about this observation is, again, it's in some contrast to the prior predictions. When we predicted what we would expect to see based on previous optical observations, we believe that the disk is being seen at a relatively shallow angle, and so the polarization degree from the disk should only be about 1%. Well, what do we find? 4%. Now, that may not sound that dramatic when I've been talking about 70% polarization, but that's a big difference, and that has strong implications for the orientation in which we're actually seeing this famous first black hole binary candidate, SIGX-1, that people have been studying for years. Instead of a 27-degree angle, this observation implies a large inclination, 75 degrees or larger. This is a bit of a challenge for some of the models, but it suggests in this case that we're looking like an inner corona, which is sort of slab-like above and below the disk, and that's dominating the polarization signal. I won't talk about this in much more detail, but it's at least intriguing, and we hope to get more observations. Indeed, we are observing this in other states as well to try to test that. And now my last object before I wrap up. Something that I'm not allowed to talk about as a discovery, but I'm allowed to talk about as a goal. And that is the black hole in our galactic center. Your local heroes, of course, produced this beautiful picture that people have gotten very excited about. But what we wanted to do with IXPE is look at the history of the black hole in the galactic center. As you know, it's, first of all, fairly pathetic as these things go. A measly 4 million solar masses. Even worse, it's been starved into submission. This thing is only emitting at 10 to the minus 6 of Eddington. It is a very low luminosity AGN. But was it necessarily always so? We suspect not, because in the galactic center region, you see a number of clouds whose X-ray spectrum indicates that what you're looking at is reflected X-ray light. The reflected X-ray light from the spectral signatures tells you that there is some bright source of X-rays in the past that lit up these clouds and that we're looking at the signal from them. Now, at present, there's no source in the galactic center bright enough to explain that, and a natural candidate would be Sagittarius star itself. So that's the project. We try to look at the clouds and we measure their polarization degree, which gives us the angle, the degree of reflection for simple scattering, and their location, which it lets us then figure out where we are in three-dimensional space, and hence the time delay. And the typical scale that we're talking about here are hundreds of years. So what we're doing is we're checking the state of Sagittarius star several hundred years ago. Now, when we proposed the mission, those clouds in the center were booming, and this was going to be a great experiment. But during the time that we got the mission together and built and launched, the clouds have all been fading. It makes it a very difficult experiment, but I will wager that it's not quite impossible, although the exposures are very long indeed. But by measuring carefully enough, we should be able to answer this question. Several hundred years ago, was Sagittarius star 1,000,000 times brighter than it is today? I think historically that's a fun thing to do. Okay, so if you've been keeping score, those are the few of you who've probably been monitoring. I didn't say anything about E, so I'll finish off the talk by pulling in that last letter. IXPE is an explorer. Now, there's some good things about it. It has no expendables. We're on the sky. We're in our second year of the PI-driven mission. And so we're getting new targets, and we're looking for variability in the existing targets. But what's probably more important to the rest of you is if I've intrigued you with some of the physics things we can do with this, think about what you might be able to do with IXPE starting in year 3. We expect, given that we've had pretty good success, that we'll have a guest investigator program. In fact, it's stronger than that. We've been, in fact, told that we will have a guest investigator program, at least to bridge us to the next senior review. So you will all have an opportunity, if should you wish, to propose for IXPE. Now, the exposures are long. I didn't go through and tell you the longest, or I think the longest single exposure has been 1.5 megaseconds. But typically we're hundreds of kiloseconds to megaseconds. Not very many objects per year. But there are more targets available. And I would think that the community, as I already mentioned, while we may have observed the best and brightest of a given source class, it's pretty clear when you look at the second and third that you're learning different things and you're learning more about the physics. So I think the community certainly can follow up what we've done, but also will probe variability and look at transients and other things. But E, it's an explorer. And if I've let you after this mission feeling a little bit unsatisfied, that, boy, that sounds great, but what the heck does it do for my galactic clusters? Or, well, I can't look at any of my CVs and do anything useful for this. And the answer is yes. This is an explorer, and the intent of explorer missions is to open up a new field. I think we've done that. We've taken you from one source to several dozen, a range of classes. We've seen some interesting physics, but it's hardly satisfying. IXPE, for the partly political reasons that I mentioned before, was strongly constrained in its design. And it has nowhere near the aperture that you would want for a serious sensitive polarization mission. We've got to get more effective area. If nothing else, some sources just very fast enough that you can't see what they're doing if you have to expose for 100 kiloseconds. I also think that better angular resolution could help tremendously. There's a lot of fine structure in those relativistic shocks, particularly in supernova remnants and PWN, that if you could dig into, you'd be probing the real physics of relativistic shock acceleration. I think that'd be great. And finally, we have a limited energy range here, and we're missing a bunch of stuff. There's a lot of interesting thermal emission from neutron stars that touch below a keV. And when you get above 10 keV, there are cyclotron lines and all sorts of features that you would like to probe the polarization properties of. So IXPE should whet your appetite. I don't think it should satisfy you. But I hope that this talk did enough to introduce you to the topic, and I thank you for your attention and be happy to take any questions.
Thanks, Roger. I'm going to grab a microphone here.
Okay.
Okay, so do we have any questions? Ramesh?
Lots of good stuff. I think you probably can hear me. Okay. Yeah, great stuff. Great talk, Roger. So many things. But when you mentioned SIGX1, and you want to change
I was worried.
change the mass estimate a lot, of course.
One does.
Right? And that estimate of the inclination, I guess, came from assuming just the reflection of from
corona.
the disk.
From the corona, in this case.
From the corona,
yeah.
but it's really the disk emission being reflected.
Yeah.
Not the jet.
Right.
So my question
Because the position angle was the electric vector is along the jet, so it's not the jet axis that we're seeing. It would have to be perpendicular fields in the jet.
Okay,
Maybe.
so you think you can rule out the jet?
Rule out is a little too strong. It is disfavored. Maybe that's a politer way of saying it. But I understand that this is a fairly radical change. And the only reason I mention it, this is a famous source that you and others have worked on for ages. I guess it's worth saying that IXPE has the opportunity to take a new look at such sources. Whether it will overthrow all these paradigms, I hesitate to say. But
I wanted one fact.
Yeah.
During the time you were observing,
Yes.
Was SIGX1 in the hard state or the soft state?
It was in the, I've got it here, make sure I've got it. It was definitely hard. We have a soft state observation that hasn't been published yet. And I'm trying to remember, are we close to publishing that one? The soft state observation? I'm sorry, I don't remember. No, it hasn't been presented to the group, so I don't think we're quite there for the soft state. I'm sorry.
It would be really interesting.
It will
to
be.
see.
And given the surprise of this, they definitely said we must look at this in the soft state. Thanks, Ramesh. Very good.
Questions, Pepe?
Well, very nice talk. Just a question on your last slide, future missions. So you advocate a bigger IXPE, maybe not IXPE, but why not thinking, since now it's been demonstrated that polarization exists, it's important to have a polarimeter in a big links type mission?
You know, that's a really good question. I mean, maybe in some sense that would be scientifically wise. The challenge, of course, is even with a big aperture, I expect polarimetry exposures to be long. And it is a bit of a specialized audience. Here we have all the world's expert X-ray astronomers, and very few have actually done polarization. I suspect that while we made an important first step, I don't think we're quite at the point where the whole community is sold to the point that they will invest the time and energy to become expert polarimeters, and therefore use up 30, 50% of something like, you know, Athena. Yeah, well, Athena won't do it, but the next big mission. It's a good question, though, because your odds of getting both large effective area and high angular resolution, that's expensive, and that's not going to happen unless a large fraction of the community is on board. I guess my fond hope is that new technologies will reduce the costs, just as new launch capabilities have reduced the need to pare things down to ridiculously small mass. And so it may be possible to make something that's not quite, you know, maybe a probe class mission, where you put together something really smart and get a cascade of energy measuring detectors behind it so that you can cover a big band. But I do think there's orders of magnitude to be had beyond IXPE. And I think there are orders of magnitude to be had with today's technology or slightly future technology. This is not 50 years in the future. If we wanted, I think we could do this 10 or 20 years from now.
Practical question. You mentioned that the effective area is small, but you never gave the number. So, and the question is, how deep can you go in 200 kiloseconds in terms of flux?
So you should think of 200 kiloseconds. I mean, it depends on the polarization degree. We got some standard formulas. There's an online exposure time calculator you can use, but ballpark, it's for 10 to the minus 12 ergs per centimeter squared per second. I think in 200 kiloseconds, it would be about 8% polarization degree. So, you know, it had to be moderately strongly polarized to have a hope, and goes down with square root from there. So, yeah, if you think about your sources, do check out that online calculator to see if it's within range. And don't be shy. Get together a team of people and ask for a megasecond if that's what you need.
Is SCOAX1 too strong to look at?
Luckily, we have a neutral density filter. We're going to take, just for completeness, a good look at SCOAX1. But it is too strong for we will fill the buffer before we could download it. So, but the plan is to do a quick SCOAX1 look, just for fun.
Statistics would be nice.
It will be wonderful, and we'll probably get a truly excellent upper limit on the polarization. At least that's our expectation. We'll see. By the way, we believe from ground-based calibration that the polarization systematics are down at the few tenths of a % level. So we haven't reached that for anything we've observed yet. Maybe SCOAX1 would. But yeah, it's worth a look.
Other questions? John?
Solar flares have strong electron beams. Are there any really active nearby stars that you would have a hope of seeing polarization?
Woof. Well, again, they'd have to get up to fluxes of kind of 10 to the minus 11 ergs per centimeter squared per second. We don't have an active group looking to M stars or anything like that, but you know, lucky things could occur. And I guess I don't know if they would last long enough for us to get on them, is the real issue. We have no plans to look at the sun itself. That would be tough on the windows.
Any additional questions, Ramesh?
If I'm permitted. So Roger, I want to go back to CAS-A now.
Okay.
You actually have a resolved image, is that right?
Yes, yeah.
And so you can tell which part is polarized. Can you separate the shocks?
Well, I'll let Pat add, because Pat is the charge of this
Can
group.
you tell whether it's the reverse shock or is it the outer shock?
You can, we have separated polarization from the outside and the inside. We see it in both places. From the Chandra images, we know that the synchrotron emission is in very thin filaments at the outer shock, okay? So we know that when we use an outer annulus around the remnant, that that's coming from very near the edge. In the interior, we assume that it's coming from the reverse shock, but we can't resolve it that well to guarantee that that's the case. I don't know what,
Radial field in both cases?
it is radial fields in
And
both
the
cases.
percentage polarization is similar?
Is similar actually in those cases, yep.
Puzzling,
Yeah.
which is good.
Any other questions? One other thing I would add to what Roger said is that these data are all publicly available now, as soon as the observations get complete and the.
Shockingly soon as the observations get complete.
That's right. So
Those of us on the team-
we're not telling you to go try and race against us, but it is true that they are available, and it is true that software to analyze them is available at the HEOSARC. Okay, well, let's thank Roger again then.
Thank you.